So let's finish up the acid-base unit by talking about indicators. Indicators are a way that when we're doing titrations, we can know when we've hit the equivalence point. We pick an indicator that has a color change where the equivalence point should happen for our particular acids and bases. So what an indicator is, and you guys have probably seen it, probably remember from your freshman year, or even last year we used them. An indicator is usually a weak acid, and it's a weak acid that has a certain color when it's undissociated, so it's still together, and then its conjugate is a different color. So just this general example of an acid-base indicator, we're saying that the acid itself, so undissociated, is one color, and we're going to say it's red. And then when it dissociates, it turns to a different color. So in this case, it turns purple. So highly acidic solutions are going to shift equilibrium to the left because highly acidic solutions are going to generate lots of H pluses. And that generating extra H+, it shifts equilibrium according to Le Chatelier's principle, and it's going to shift it back towards the reactant side, so the undissociated acid, which is going to be red. And so in a highly acidic solution, it's going to be red. But then, as we slowly add hydroxides to the system, that's going to decrease the amount of H+. And so as we decrease the amount of H+, so if we take H+ away from the system, Le Chatelier once again says it's going to stress the system, and it's going to stress the system, causing it to shift now to the right, to reestablish, to refill in those H pluses that we've taken away. So as that happens, it's going to shift to the right, and it's going to start predominantly being this color right here. And so eventually, when we get a higher ratio of this color, of this conjugate, it's going to turn purple in there. And usually the ratio for when it changes from one color to the other is 1 to 10. Okay, so when we have a 1 to 10 ratio, it's going to change in colors. So in a highly acidic situation, we're going to have 10 of these for every one of those, and it's going to appear red. But as we shift equilibrium this way, and we have 10 of these for every one of those, it's going to appear purple. So the trick is just picking an indicator where this shift from red to purple happens about the same place as our pH change, or as our equivalence point. Okay. And remember on those titration curves, so it's a very, very steep change when the pH changes, so we've got a large shift in pH, and so that change in color from one to the other is very distinct. It's not that you're going to wind up with a slightly red, slightly purple solution because it makes that huge jump up in pH. That means that it's going to be one color down here, so it'd be red down here and it'd be purple up here. And you don't really spend much time in that distance. So if we just sketch a titration curve right there. Okay, so that shift is going to happen right there somewhere in that jump. And really the distance between these 2 points on the x-axis is very, very small. And so it's like a couple drops. Or I mean less than a drop, a couple of molecules that cause that shift. And so we're not able to actually see anywhere in between there. We just know that it changed from red down here to purple up here. Okay, but we don't get any middle ground. And so it's the key of picking a good indicator is one where it makes that color change over this distance right here. So here's a couple different indicators when they talk about the pH range of end point. This is the pH when the color changes. So for example, phenolphthalein, that changes from clear to pink. And so when the pH is between about 8.2 and 10, it'll switch from clear to pink. So it'd be clear and then pink. And so if you were doing a weak acid, strong base titration, where the pH change or the equivalence point is above 7, phenolphthalein is pretty much the standard choice because your equivalence point, you know it's going to happen above 7. And so a clear to pink change at 8.2 to 10 is about right where you want it. If you're doing a strong acid, strong base, bromethymol blue is usually a good choice because its change happens right around the equivalence pH of 7, around a neutral. So if you're doing a strong acid, weak, strong base titration, the equivalence point is going to occur at 7. You should know that. And so if you're trying to pick what indicator you would use, you would want one that's going to have a change around 7. So it should flip around 7. And so bromethymol blue is a good choice for that. Bromethymol blue starts yellow in an acidic solution, turns blue in a basic solution, and it makes that transition right here in the middle. Okay, and so you can see that at exactly a pH of 7, it's going to be a mix of yellow and blue. But remember, when we're doing a titration, see this giant jump up? So it's going to go from yellow instantly to blue. We're not going to see really that transition right there, where it's kind of in the middle. It's going to be yellow, 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 blink, it's going to be blue. And it'll turn to blue and stay blue as long as it's basic. So when we draw these colors in here, it's yellow and it's blue, all yellow down here and all blue up there. And so it's not like the blue disappears once it gets up to that pH. The transition just happens somewhere in this range right here. Right, if we're doing one like acetic acid and sodium hydroxide, that's going to be a weak acid, strong base. So your equivalence point is going to happen around 9.1. So a good choice for that one is going to be the phenolphthalein. And you can see phenolphthalein goes from clear, or clearish, to pink, right up there, where about the equivalence point is. And so you wouldn't want to use something like the bromethymol blue because it's going to make its change somewhere down here. And so that's not going to be anywhere near our equivalence point. We're going to use this guy, and once again, it's going to be clear, 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 pink, as it jumps up here into the basic range. So we're not going to see this middle ground area. We're just going to see the change from clear to solid pink. Then, unfortunately, we're not always given the pH range for an indicator to know when it should happen, and we don't always really know what the color changes are going to be for a given indicator. So the way you would tell instead is you use the pKa of the indicator to help you figure it out. So remember, all the indicators are just weak acids, so they're going to have a Ka value. And if you just take the negative log of their Ka value, you want one that's really close to the pH of our equivalence point. So if we look back at our example here, the pH, the equivalence point was 9.1, and so you're going to want to get you're going to want to get an indicator that has a pKa approximately 9.1. And the pKa of phenolphthalein is 9.7. Okay, so the negative log of the Ka for phenolphthalein is 9.7, and so those two, in this case, the pH is approximately the same as the pKa, and that makes that a good indicator choice.